All right, hey there, Precalc. So today we're starting a new chapter. We're starting our chapter on polynomials. And we have been studying quadratics, and quadratics are actually just a specific type of polynomial, a polynomial with degree 2. So I'm going to write something here, and it's going to look kind of fancy. But what is a polynomial? So a polynomial is always of the form, okay, a leading coefficient, I'm just going to call it a sub n, times x to some power n, okay? And then there's another term. I'll just call the next coefficient a sub n minus 1 just for the second coefficient. Then x is to the n minus 1 power, and we just keep working down. Notice I'm subtracting a power of x each time I go, and I just do this all the way down till I get to the end, and my last one is going to be a sub 1 times x to the first, and then our last term is just going to, I'll just call a sub 0. Okay, so when we talk about quadratics, something like 3x squared plus 4x plus 5, this is a polynomial. Notice there's a coefficient times x squared. Then there's a coefficient times x to the 1 less n minus 1. Okay, this is to the first. And then lastly, there's an x to the 0 here, which we just don't write. So polynomials have coefficients and x to some power. So let me write an example of another polynomial. Negative 2x to the 7th plus 3x to the 6th plus 4x cubed plus 1. Okay, this is still a polynomial. Now, why here, notice x goes to the 7th to the 6th, we're subtracting 1. There's no x to the 5th. Well, really, there's a 0x to the 5th, and we just don't need to write it. So it's not like you need a term for every power of x. Sometimes those terms are just 0 because the coefficient would be 0. Now, polynomials, these n's, okay, these powers, they have to be whole numbers. We can't have a x to the 1.5. That's no longer a polynomial. That would be a radical type of function. But these are what polynomials look like. And what I want to do is I want to take a look at the end behavior, okay, of polynomials by looking at the degree. So let's just jump into Desmos here a little bit. Okay, and let's start, okay, with something that we know, x squared. Okay. When I say end behavior, what am I talking about? Well, I'm talking about what's happening at the ends of the function as x goes to infinity and as x goes to negative infinity. Where are the y values going? Now, to simply put it here, they're both going up, right? The end behavior is they're both going upward. Okay. Whereas if I put a negative here, they're both going downward. Okay. Now, how would I write that they're both going up? I would say, here, let me just do this. Okay. The end behavior for this one, I would say as x goes to infinity, that's to the right. F of x, which is y, goes to positive infinity. As x goes to negative infinity, that would be to the left. F of x also goes to positive infinity. It goes up. Okay. Now, if I put a negative here, now both of the statements, okay, would just be they go, f of x goes to negative infinity. So end behavior for a quadratic, either they're both going up to positive infinity or they're both going down to negative infinity. Now, what happens as I change the degree? Well, if I make this a third degree, now we see that they're going opposite directions. As x goes to infinity, f of x goes to positive infinity. As it goes to the right, it goes up. As x goes to negative infinity, so as we go to the left, f of x goes to negative infinity. It goes down. Okay. Now, what happens if I put a negative in front? We know that's going to reflect it. Okay. So it switches that way. Okay. Now, as x goes to infinity, f of x goes to negative infinity. As x goes to negative infinity, f of x goes to positive infinity. Really, it's just about lefts and rights and up and downs. Okay. Now, let's keep going up. Well, what happens if I make this an x to the 4th? Okay. It kind of reminds you of x squared. They're both going up, and if it's a negative, oops, If it's a negative, get my negative in the right spot here. There we go. They're both going down. Okay. How about x to the 5th? That reminds me of x cubed, right? Now we're going this way. Whoop, match. There you go. That matches the computer. Okay, going this way. Okay. To the right is up, to the left is down. A negative would flip that. What about an x to the 6th? An x to the 7th? An x to the 8th? An x to the 9th? An x to the 10th, and so on. So what we notice here is when the power is even, they both go in the same direction. Either they're both going up, so let me go back to the 8th. They're either both going up, or if there's a negative in front, they're both going down. If it is an odd exponent, now they go opposite directions. So in this one, it's going like this. Okay? But if I put a negative in front, now it flips, and it's going like that. All right, so I tend to do a lot of these body things, right? Up, both down, okay, this way or this way. Okay. Now, how do I remember when they go opposite directions, which way they go? If it's positive, from left to right, it goes up. Okay? Just like if it were a line, right? This line has a positive slope. So from left to right, it goes up. By the way, this is x to the first. It still matches our pattern where they go in opposite directions. It's just linear now. Okay. So what if I have an x to the 7th? Okay. But then I have some other stuff here, like an x to the 4th. Okay. And maybe an x squared. Okay. Now there's some extra stuff happening in the middle here, but this is still an odd degree polynomial. The biggest power is odd, so it goes in opposite directions. There's some extra stuff that happens in the middle, but it still goes in opposite directions. Okay. Now, what if there's an x to the 6th? Okay. And let's make this maybe a minus 5x to the 3rd. And let's maybe subtract x. Okay. So again, there's some kind of weird stuff happening here in the middle. It no longer just kind of looks like a parabola. Okay. There's kind of an extra little, I don't know, little hill there. Or sledding down this hill or something. But notice, the leading coefficient, the first term is to the 6th power. This is an even polynomial. They're both going up. Whereas if I put a negative there, now they're both going down. So this is the end behavior patterns that we see. Okay? And I'm going to make a little chart here, okay, that shows it. So for a polynomial with degree n, okay, the degree is the biggest exponent that we see. Okay? If n is even, they're both going in the same direction. If n is odd, they're going in opposite directions. Okay? So now I'm kind of breaking this to even and odd, and then the leading coefficient. Is it positive or it's negative? Well, if it's even, x squared, x 4th, x to the 6th, x to the 8th. They're going the same direction, and if it's positive, they're both going up. So it's going to go up here, and it's going to go up here. Now, it might just be like a nice smooth parabola, okay? Or there could be some other funky things that are going on in there, okay? But we don't care about that. We're only talking about end behavior. So I'm just not even going to write anything. I'm going to put an arrow up to the left and an arrow up to the right. And the way I write this is as x goes to infinity, that's to the right. F of x goes to infinity, that's up. As x goes to negative infinity, that's to the left. F of x goes to positive infinity, that's up. Now, if the degree is even, but the leading coefficient is negative, now they're both just going to be down. And I'll write that as x goes to infinity, that's to the right. F of x goes to negative infinity, that's down. As x goes to negative infinity to the left, f of x goes to negative infinity, which is down. Okay. Now for the odds. If the leading coefficient is positive, it's up to the right and down to the left. Okay, there could be extra goofy things happening in there, okay, but we don't care about that. Again, we're only talking about end behavior. And I'm going to say as x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x goes to negative infinity. You might be asking, do I really need to write all that? Yes, this is how you say that. That's mathematically how you describe the end behavior. Okay? We don't just use lefts and rights and ups and downs. We communicate this way. Lastly, if it's an odd degree polynomial but it's negative, we know it's going to be just reflected. So it's going to look something like that. Up to the left, down to the right. As x goes to infinity, f of x goes to negative infinity. As x goes to negative infinity, f of x goes to positive infinity. Left, up, right, down. So, okay, as we take a look at this, determine the end behavior of each polynomial. So I'm looking at this. What degree is this polynomial? What's the biggest exponent? 3. It's a third degree polynomial. That's odd, so I know they're going to go in opposite directions. It's either this, okay, or it's that. Well, what's the leading coefficient? It's positive, which tells me it's going to be something like this, followed by something like that to the right. So I write, as x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x goes to negative infinity. Okay. Number 2, what degree is this polynomial? Biggest exponent? 4. So that tells me either they're both up or they're both going down. Leading coefficient? 1/2. That's positive. So it's going to be up and up. As x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x goes to infinity. Okay. All right, how about this one? Degree 3, odd, opposite directions, either this or this. Okay. Leading coefficient is negative, so that tells me from left to right it goes down, so it's going to be like this and like that. As x goes to infinity, f of x goes to negative infinity. That's this one. As x goes to negative infinity, f of x goes to positive infinity. All right, number 4. What's the degree on this one? Biggest exponent? 4. Even. Either both up, both down. Leading coefficient, what's in front of that? I see a negative. Okay, that tells me both down. So it's going to be something like this, something like that. As x goes to infinity, f of x goes to negative infinity. As x goes to negative infinity, f of x goes to negative infinity. Good? Okay. And again, if you need to graph these, go for it. But hopefully we're kind of figuring out this pattern here. The degree, even or odd, and then if the leading coefficient's positive or negative. We had to be careful. Number 4, the leading coefficient is -1. Okay, it's just written out of order. Okay. Little side note. Have you ever noticed that the infinity sign kind of looks like a Pringle? See it? Right? So this part's like the top, and then this part you can kind of like see underneath it. Yeah, get it? Okay. Make you hungry? Maybe. All right, so we're just talking about the end behavior. Okay? We're talking about what happens over here and what happens over here. Okay? Well, now we're going to spend some time trying to figure out what's going on in the middle. And there's a lot of things. So let's talk about extrema first. We've talked about minimums and maximums. Okay? And what I want to show you guys, okay, is, well, let's go back to just our x squared. This is what we already know. How many extrema does x squared have? Okay? It has just one, right? There is one minimum. Okay? But what if I have something like x to the third? Well, if it's just x to the third, this doesn't have any extrema, but let me add or subtract and make this third degree polynomial just a little more interesting. I might have to play around with this just a little bit to get some. There we go. Look at this. So third degree polynomial, and this has 2 extrema. It has one relative maximum. It has one relative minimum. Okay? And as I play around with this third degree polynomial, you saw me do that a little bit. This is the most turning points, okay, the most extrema we can have. I use turning points sometimes, and the book does, because when a turning point, it goes from up and it turns to go down, and then it's going down and it turns to go up. So turning points can be used instead of the word extrema, so just be aware of that. That's the most I can have, right? My end behavior tells me it has to be this and it has to be that. Well, this is the most turning points I can have. Now, how about a 4th degree polynomial? Okay. Well, right here, you can see this has three extrema: a relative min, a relative max, and a global min. And this is the most extrema that I can have. It doesn't have to have that many. Okay, so when I change that to a minus, now I only see one extrema. Okay, there's one global min, that's it. But when this was a plus, there was actually three. So if I could continue to show this, but I'll just put this up here. A polynomial can have at most n minus 1 turning points. If it's a fourth degree polynomial, it can have at most 3 turning points, 3 extrema. It's a fifth degree polynomial, it can have at most 4. Doesn't have to have 4. Could have 0. Okay? But this is the at most is kind of a key part of that phrase. Can have up to that many, one less than the degree. Okay? Now let's talk about x-intercepts and zeros. And let's take a look here at the zeros of this function. F of x equals x minus 4 times x plus 1 squared. Okay? And let's rely again on what we've learned with quadratics. If I had a quadratic, and we looked at a lot of these, let's say it was just x minus 2 times x plus 1. What are the x-intercepts? Okay, well, they would be 2 or negative 1, because we set it equal to 0. And we use the zero product property, and we say x minus 2 equals 0, or x plus 1 equals 0, and we get those two solutions. Now with this one, when we set 0 equal to x minus 4 times x plus 1 squared, x minus 4 equals 0, or x plus 1 squared equals 0. This gives me a solution of 4. This gives me a solution of negative 1. Okay? Right? If I take the square root of both sides, it's still 0 over here. X plus 1 equals 0. Remember, another way to write this would have been to say this is x minus 4 times x plus 1 times x plus 1. So our solutions are 4, negative 1, or negative 1. It's just this negative 1 is repeated twice. Okay? Or you'll see the word multiplicity. It's negative 1 and it has multiplicity 2. Okay? So I use the word zeros here, but they're really x-intercepts. Okay? Same word. Okay? Here, what are the x-intercepts of this one? Well, this is really x minus 2, x minus 2, x minus 2 because it's cubed, x minus 6. So what are the x-intercepts on this one? 2, but it's repeated. Okay, I said this one was repeated twice. Is it repeated thrice? I'll just write repeated 3 times. Okay, or I could say multiplicity 3. Okay, and our other x-intercept is 6, which is just multiplicity 1. Okay, now I want to show you something really interesting that happens with the graphs, okay, of these, okay, with these repeated zeros. So let's do x minus 4 times x plus 1 squared. Okay. Now, something interesting happens. Okay, our first x-intercept is 4, and we're just cruising right through. But notice what happens at the x-intercept of negative 1. Okay, it comes up and it touches the x-axis and goes back down. And here's something that I want you to kind of look at. Okay, compare this to x plus 1 squared. That would be a parabola where the vertex is on the x-axis. Okay, and in fact, if I put a negative there, it kind of looks like that part of the graph that we had when we had the x plus 4. No, it was x minus 4, wasn't it? Is it x minus 4 or x plus 4? X minus 4. There we go. So I say that this repeated twice comes down, touches that x-intercept, touches that 0, and reverses paths and come back up. It's kind of like there's a vertex there, but it's not a parabola, it's not a vertex. But we have an extrema on the x-axis. Pretty interesting. If I would have made this to the 4th power, the same thing happens, or the 6th. Okay? Now we just had squared, but the x minus 4, that's just to the what power? That's to the 1st, and it just goes right through that x-axis. But if I would have made that to the 2nd power, notice what happens there. This x-intercept, again, also comes up, touches the x-axis and reverses directions. I call this a bounce. Like it's coming up, it hits the x-axis and then bounces back. Comes up, hits the x-axis, and bounces back. Okay? So I'm going to say if it is, let me make this to the fourth power now. Okay? So on this x minus 4, it's bouncing and coming back, or at -1, it's bouncing and coming back, and same at 4, because these are both repeated an even number of times. Their multiplicity is an even number. Okay? Now what if we have, an odd multiplicity repeated like 3 times, like x minus 2 cubed. Okay. Now notice if I just put that in here, we know this is just x cubed translated right to. And what happens? It kind of comes through and snakes through. It acts like it's going to maybe bounce, like if it was squared, but instead it snakes its way through just like an x cubed function does. But then there was another 0. It was x minus 2 cubed times x minus 6. Okay. And we see x minus 6, it just flies right through that x-axis. But where this x-intercept of 2 is repeated 3 times, it acts like a cubic function. It comes down and what I call it snakes through. Okay, it starts to change the concavity. Okay, it goes from concave up to concave down, kind of like an x cubed function. Now, if this was to the 5th, it would still act the same way, and the 7th. But if it was to the 2nd, it bounces. Okay, 3rd, it snakes through. Now, I could have that one snake through at 2, and then I could have this one bounce at 6. So it snakes through because this 0 is repeated 3 times, and it bounces at 6 because that's repeated 2 times. Okay. So here's what I'm going to say for even and odd powers of these factors. So if I have it factored and I have some exponent here, if it's even, it intersects but does not cross the x-axis. I call that a bounce. Okay. B-O-U-N-C-E. It bounces. That could either look like this, where it comes and it touches the x-axis and goes back up, or it comes from the bottom, touches, and goes back down. That's a bounce. Okay. Now, if it's odd, well, first off, if it's just 1, it goes right through. Right? So, I mean, it's just going to cruise right through just like any old normal x-intercept that we're used to seeing. But if it's odd and bigger than 1, so if it's repeated 3, 5, 7 times, it is going to snake through. Okay? It's going to act like an x cubed, which could either mean it comes like this and then switches. Okay? Notice it goes from concave up to concave down, or it goes from concave down to concave up, like that. Okay. So when we have the zeros and we have it factored like I do here, we can put together a lot of information about what this graph is going to look like. And that's what we're going to finish up with. We're going to finish up with a couple sketches of functions. So let's sketch the function x cubed minus 4x squared plus 4x. Okay. Well, first thing I want to consider is the end behavior. Okay. Now, it's odd, and the leading coefficient is positive. Okay. We know that looks like this and this, right? We had that discussion in the first part of this video. As x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x goes to negative infinity. So when I look at my graph, okay, I don't have a lot of details, but I do know it's got to end down there, or it's got to be like that down there, and it's got to end up there. Okay? Now we've got to kind of figure out what's going on in the middle, and then we'll sketch it all together. And finding the zeros is going to help us with that. So I want to see if I can factor this. Okay. Well, I notice there's an x in everything. Remember, first step at factoring out the GCF. So let's factor out an x. And we have x squared minus 4x plus 4. Now, can I factor what's remaining? Yes, I can. Notice this is x minus 2 or x minus 2 squared. So what are my x-intercepts? X equals, this one would give me an x-intercept of 0. This one gives me an x-intercept of 2, but it is repeated twice, or multiplicity 2, depending on how you say that. So, from my graph, I can come back here. I know the end behavior, but now I know that I have an x-intercept at 0, and I have an x-intercept at 2. But this one is repeated twice, and what did we say? If it's repeated twice, it should be a bounce. There we go. So now can I put the behavior at the x-intercepts together with the end behavior to make a graph? Well, I know I have to start down here. Okay? And I'm not interested in a lot of details. I'm just talking about a general sketch of the graph that includes the end behavior and the zeros. So it's got to start somewhere down here. Okay? Go through that x-intercept of 0. Now my next intercept is here and it has to bounce and I have to finish up. So it's got to come back down, bounce at 2, and go back up. Okay? Again, I'm not looking for a lot of detail here, only end behavior and x-intercept behavior. Okay, I've got it. Okay? Now I don't know, it could go way up there, way down, bounce and then up. We're not sure. Like I said, I don't care about those details yet. Okay? All I care is about the general sketch of the graph. So let's check this one out. Let's see how we did. It was x to the 4th. No, x to the 3rd. Minus 4x squared. Plus 4x. And did we get the general shape of the graph right? Yeah, we've got the end behavior. We had it coming up through x equals 0, coming back down, bouncing at x equals 2, and continuing up. So that's what I'm looking for here. I'm looking for you to put together, okay, the end behavior with the behavior of the x-intercepts to give a sketch. Okay, so do the best you can. That's an introduction to polynomials. They're really fun. We're going to learn a lot more with these. We're going to put together more details, but that's a good start for today. Thanks for watching.